This presentation is titled Number Theory Neat Examples Set 4. My name is Anton Antonov. Today is July 26, 2025. I started this presentation in February, like 4 months ago, 5 months ago. It is about Prime-phi, divisors, and torsion function. Somebody might say, well, maybe these are the functions we should first talk about, not in set 4, but maybe in set 1. Well, anyway, what are neat examples? Neat examples are concise and straightforward code that produce compelling visual and textual outputs. We are going to showcase Raku programming here in this presentation. We're showcasing more precisely the packages math number theory, in which the number theory computations are done, and the graphics package JavaScript D3. So this is this here, what you see is the Jupyter Notebook framework in Visual Studio Code. I'm using Raku chatbook, and so JavaScript graphics like this one code is being readily rendered, right? So this is what is happening. I have described this in more detail on some other presentations. So first, let's talk about Prime-phi. Prime-phi gives the number of primes less or equal than the argument. It's also known as the prime counting function. It has this nice expansion, and this here is a graphic which shows this expansion. So these are approximations of so-called logarithmic integral, and so we can look at the Prime-phi theorem for more details. So we can visualize this with the Ulam spiral, and let me see, where is the Ulam spiral here? Yeah, well, Ulam spiral, again, I featured it in some other presentations. It's one of the standard things to do. It's a way to embed or display primes in this two-dimensional kind of setup. I can use probably somewhat different color palette, but let's see, it's going to be more compelling. Yeah, actually probably looks nicer given the background here, but I'm going to return to rainbow because I use turbo a lot. All right, so let's actually do something more interesting. This is a relatively new function in JavaScript D3, angle path. So we give different, as arguments to angle path, we give different angles with which a turtle graphic is being produced. If I use a somewhat different breakdown, we might get somewhat different visualization. With a larger number here, we might get something more compelling, and maybe I should have tuned the height. Let me actually do that, and I'm going to probably put something here. So let's actually do this. So yeah, I can observe, of course, the summary of the coordinates which are being produced. These are the two-dimensional Cartesian coordinates after using this angular path. This is, again, as I mentioned, related to turtle graphics. We can get this kind of nice compelling results. This might be a little bit too slow, but let me actually do one more attempt here with say 1000, see what is going to happen. So I think the whole thing starts somewhere here, right? So we can, I can probably convince you by using the axis here. And so yeah, so we start at 0, 0, which is somewhere here, and then we go around. All right, so next function is divisor sigma. This it's denoted with in this way, sigma symbol, then k and n. So let me tabulate some results here. So the numbers, the second argument is here in this column, and these are the k arguments, right? And so we can see here that we're putting these divisors to those numbers in different powers, and this is what are the sums we see here. All right, so let's actually plot divisor sigma for different inputs, and again, in this particular case, I went for like relatively larger number, 150, but yeah, this is probably pretty informative. So we have the number of divisors, the sum of the divisors, and the sum of the squares of the divisors. All right, so there are a variety of applications of divisor sigma. It's Here actually we find the so-called amicable numbers, pairs of amicable numbers. These are two different numbers in which the sum of the proper divisors of one of them equals the other number, right? So the proper divisors of 220 equal the sum of them equal 284 and the other way around. So there's a faster way of doing this. So instead of say 300 numbers and Cartesian product, you can see that I'm actually pre-computing the divisor sigmas for this 3000 numbers. Then I'm just kind of querying the sigmas, so to speak. And I'm producing the combinations. The actual function combinations or sub combinations method in Raku is very fast. And so, and you can see we have like say approximately 4,500,000 pairs. And you know, we found this amicable numbers here. We can also use the Ulam spiral, as earlier was discussed, sunflower embedding. This actually it's probably more compelling. I mean, I'm using the Ulam spiral embedding because, well, I mean, we actually see some patterns which you usually see with the primes. But Ulam spiral is used so much that, yeah, well, I'm not going to focus on it. With the sunflower embedding, that's a little bit interesting. I spent actually some time trying to figure out which parameters to use here, to logarithmize, to round, to whatever, right? But I mean, I would say this produces somewhat compelling diagram. Maybe I should zoom to kind of show it, yeah. And I'm going to produce some other version of this using bubble charts below. But before that, let's talk about the torsion function. The torsion function phi n, it's also called the Euler's torsion function, is defined as the number of positive integers which are less than the argument and they're relatively prime to it. And so it has, I think Euler himself, he used the sign pi, not the sign, the symbol pi. But Gauss used phi, and I think that's why we say Euler phi. With the expansion of Euler phi into series, we can introduce, or it's one of the ways to introduce mathematical analysis into number theory. It's very interesting in general. So here we can plot the Euler phi for the first 100 numbers. And yeah, there's some asymptotic expansions. You can look at some dedicated articles about that. Let's actually plot this Euler phi for a much larger sequence of numbers, and we basically exemplify this formula here. We want to show that this asymptotic kind of holds, and we can see it somewhere here. All right, so again with the Ulam spiral, producing some symmetric kind of pattern here, which is probably compelling. Similarly, we can use the Klauber triangle to visualize some kind of Euler phi, you know, with some kind of transformation here. So again, Ulam spiral, Klauber triangle, they used to display primes. And let's look at some numerical, more numerical example here. So we're trying to figure out what are the solutions of this equation, right? The Prime-phi when it equals the Euler phi. And this happens only for these 8 numbers. This can be proven, but instead of using a proof, we're just going to plot the numbers here. Like look at the graphics, and you can see we have some intersection somewhere here. Let me actually change this. Here, yeah, all right, well, yeah, more or less we see these results here. All right, so as I promised, I'm going to show some bubble chart, sunflower embedding for the divisor sigma, and so I actually need to zoom here. So what is happening? So first of all, I think this is a very nice plot, right? It has this kind of shaded version of the bubbles. They seem to be overlapping. They look metal or plastic, and kind of it's a nice kind of setup. So what is happening here is that the sunflower embedding is being called for the first 2000 integers, and divisor sigma, this is with the squares, again logarithmic and etc. The size of the bubbles is determined by this expression here. So the group here is being, it's a string. So if I show you what the sunflower looks like, right? It's, yeah, I mean, we basically have, it's It's a list of, it's a data set, if you will. It's a list of hash maps in which we have the keys group X and Y. And I'm adding here, I'm adding a fourth element, right? I'm putting the Z value, which is in this way, and this determines the size of the bubbles. And I think the result is pretty compelling. All right, this was it. Thank you for your attention.